set things up. Where is this? Okay. What Windows? Where is it? Is it? You guys, you don't need it. Trust me, you don't need it. This MacBook Air M1 is like way more powerful than 99% of the market. Like I said, MacBook Air M1 is a really good laptop for the price and everything. No. Don't buy cheap laptop. If you use Mac, you see the touchpad and the keyboard. At least as a programmer, you should invest in your mouse or touchpad and keyboard and your chair. That's what you should be investing in. Okay. Not this one. Let me. What's the lecture number though? 10? 11? 11? Okay. I'll see that this is 11. Lecture 11. Okay. So today we're going to learn something which is called integral bound, asymptotic behavior, and what's the other one called? Recurrence, which we're going to do it next time too. We're going to do it here and then we're going to do it another time. When is the next scamming session? I don't know. Today is more mathy than usual, but it's easy though because it doesn't require so much imagination. Okay, so let's think about this. The first thing is integral bound. Let me try to, not really, not much proof today. More like things I want to get out of the way. Okay, so we learned, right? If you add 1, 2, 3 plus 4 plus blah 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 up to n, right? It's like n plus 1 over 2 or something, or minus 1. I don't remember. N plus 1 over 2, right? Is that right? I think so, right? Right, n plus 1 over 2, right? But and you see that if you square this, you have something, right? You have some formula which I don't remember. It's something multiplied 3 times and divide by 2, and also if you do it cube, and so you have that guy square, right? You prove it in the homework. But those are the questions that I can ask you because there's a closed form for it. But let me try to tell you that most of the sum do not have a closed form. So for example, let me show you. 1 plus 1 over square root 1. Oops, sorry. 1 over square root 1 plus 1 over square root 2 plus 1 over square root 3 plus 1 over square root 4 plus 1 over square root 5. Oops. Plus dot, 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 plus n plus like 1 over square root n. That thing, as far as I know, no closed form. By closed form, I mean something that you can plug n in and then you get the answer right away. Okay, there's no closed form formula. Oh, that's why it sounds weird. Again, I forgot to connect my headphone. That's why my headphone sounds weird. Let me check. Okay, right microphone, right headphone. Okay. If you said something in the last 10 minutes, I cannot hear you because I did not turn on my headphone. Sorry about that. Okay, so the goal, I convince you there's no closed form. You can try. There's no closed form. As far as I know, maybe if you are really smart and you figure out, tell me immediately like, what's the closed form for this guy. Okay. And my iPad doesn't change anymore. What happened? Okay, seriously. Okay, now it's back. So if my screen seems freezing, let me know though. I update the new iPad OS and it seems keep disconnecting me from the what's that called? From the computer. It keeps disconnecting me. So here's the thing that I want to do, right? I want to say that okay, even though I have no idea what the sum is, I want to be able to tell. Since we learned the notation already, sum from I equals to 1 to n of 1 over square root I. Okay, I want to bound it. This is what I meant by bounding. Okay, I want to say it less than something, which we're going to call upper bound, and it's going to be greater than or equal to something, which is we're going to call lower bound. Okay, right? And you know that this bound should at least scale with some function of n, right? That n is over here. That n is over here. Sum of it. At least I know that maybe someone found it, except I don't know, or maybe no one has found it. Sum of the proof, sum of the sum, you can actually prove that there's no closed form. As in like basic algebraic function. The proof for this kind of thing is kind of weird. The proof that you cannot find a closed form for something is kind of weird. Okay. But that's good. That means you start to not believing what I said. So you're now requesting a proof for what I said. Okay. But here's what we want to do. A lot of times, this is much easier than the other way. Finding the closed form is typically hard. Okay. But if we want only the upper bound, lower bound, it's much easier. Anyone has a good idea? Anyone has a good idea? How would we find a lower bound or upper bound? Anyone has a good idea? Anyone? Let me help you. Let me help you. Let me help you. Okay. So I'm gonna draw something. This is 0. And let me draw something. This is 1. 1 over square root 2 is less than 1. Okay. So 1, 2, 3. Oops. 2, 3, 4, 5, 6, 7. Yes, we're gonna integrate. But wait 2 seconds before I finish. This 1 over square root 2. This is 1 over square root 3. This is 1 over square root 4. This is 1 over square root 5, and so on. Did you want to go to grad school? You cannot avoid math. You cannot avoid calculus. You cannot avoid calculus, right? So I think the way calculus was taught at the beginning, it hurts a lot of students. A lot of students hate calculus because they don't know what it is for. It's actually for everything. It's actually for everything, but you're gonna discover that like after you fail the class or so on, right? So let's do this. So Justin said integrate. Why? So first, when you say integrate, did you see the sum? This sum, where is it on the graph? Right? What I'm drawing is like a bar chart, right? It's like a bar chart. Where is that sum in the graph? Can anyone see it? No. All of them. Where physically is it in the graph that I drew? Very good. What's it? Is the area. Think about this. Each stick, right? The width is 1. Right? The width is 1. Therefore, this is the area, that's the area, that's the area. And then if you ask the total area, that means you add up all these numbers, which is exactly the sum. Right? So in particular, the area of all the stair, the area is going to be the sum from I equals to 1 to what number? Can you tell me what's the number up top? What's the number up top? 6 or 7? 7, right? Up to 7, right? Because if you just draw 1 over square root 6, 1 over square root 7, and so on. There you see. Okay, now, finding the area of this stair looking graph is hard because you need to do the sum to find the exact length. Can you guys approximate it from me though? Can you guys approximate it from me somehow? What would you do? And I need to change the color. Did I want the color? Right? You know that finding this is hard, right? But Justin said earlier, if I know some continuous function that sort of does the job, then that would be better, right? That would be better because you integrate is easier than finding the sum. Anyone? That's a good idea. Can you bound it from the above? Can you bound it from the above with some function? Can you bound it from above with some function? Anyone? Okay. If not, let me help you. What about I claim that the area under the brown chart, this thing actually diverges. So if you sum to infinity, you're going to get infinity. But the brown chart is less than the green one. Are we good? Right? Everyone agree, right? That this thing is less than the green curve. Right? That the area has to be less than the green curve because it's strictly more than the other guy. Are we good? Okay. Are we good? Right? So that means if we can find that green curve over here, the area under the green curve, we have the upper bound. Good? Right? So to find the area under the green curve, what do we do? What do we need to do? What do we need to do to find the area under the green curve? We need to integrate. Okay, good. So the upper bound is some sort of integral, right? Integral of what? Right? When you try to do the integral, you need 3 things. You need the limit, and you need the actual function. Okay, and okay, I can fill you in for dx. Okay, so help me fill in 3 things, right? the limit, and the function itself. Okay, but first tell me the function. What is the function of the green thing? Okay, let me call it fx. Yeah, what's the green function? What do you think? Can anyone tell me? Or anyone have a good way to figure out the green function? Let me ask you something easy, and then you're gonna figure out what the function is. What is f of 1? What's the function when you plug 1 in? What do you think it should be equal to? It should be equal to 1. What about f of 2? Yeah, 1 over square root 2. F of 3 is what? I think you can guess, right? And now I'm going to ask you, what is f of x? Yep, exactly that one, right? Then you might have some question about whether it's 1 over square root x or square root x minus 1 or square root x plus 1. What I recommend, just plug it in a few values and then you're going to see what it is. Okay, 1 over square root of x. So now we have this part that this thing is 1 over square root of x. Okay, but you can see this function sort of have two things, right? It has the first part over here. It has the square part, and actually let me use purple. Okay, and it has that part. Okay, right? It has the first piece and the integral part. Can you tell me the limit for the integral part? Right. So we're gonna integrate from here to there. What's the limit of the integral? From what to what? From 1 to 7. Okay, so the right hand side, don't worry about how to integrate because you know how to integrate. It's just a polynomial, right? But the idea here is important that you turn the problem into a calculus problem that is much easier to solve than solving the sum, right? Right, it's a number, don't worry about it. But we need to do one thing, right? We need to add up the first piece over here, right? The first piece over here, okay, the area is clearly 1. Okay, so that's good. Any questions about how to set things up though? Any question about how to set things up? Be careful, do not memorize the formula though. Do not memorize the formula. If you need to do this, just do it again because you have to do something different for the increasing and decreasing function. You have to do something differently for increasing and decreasing function. If you memorize it, you can be screwed up whether it's x plus 1 or x minus 1 and so on. You mean yes, just redraw the graph, do the exact same exercise. Okay, increasing function and decreasing function, you need to do something different. Okay, just draw the graph, you can get it in 10 minutes, like geometric sum. I told you not to memorize because you can screw up whether it starts with 0 or 1. Okay, so let me summarize on the next page. Right? 1 over square root I sum from I equal 1 to 7 of 1 over square root I is less than or equal to 1 plus the area, which is the integral from I from x equals to 1 to 7 of 1 over square root x dx. Okay, now I want to be a little bit more fancy. This is what I'm going to do. I'm going to change 7 to n. That's all. So it's more generic. You can guess, right? This is going to happen. Okay, but when you try to do the concrete one, that's easier because you can figure out whether it's n or n plus 1 and so on. Okay, any questions so far or any questions so far? Okay, the right hand side we can calculate it easily, right? So this is our upper bound. It's going to be less than or equal to 1 plus, what is this? Minus a half. Wait. No. What do you get? So it's x minus 1/2. So add 1. So it's going to be 2 x to the 3/2, right? X to the 1/2 from 1 to n. Did I screw things up? I did not, right? which is equal to, well, which is equal to 1 plus 2 plus square root of n. Did I screw things up? Did I screw up the sign? Wait. I did. Sorry. 2 square root n minus 2. Okay, that's better. Okay, that's better. Okay, so that means it is equal to 2 square root n minus 1. Okay. Any questions so far though? Any questions so far? Okay. Then you get 1. You have another 1, right? You need the lower bound. Okay. Any questions so far though for upper bound? Any questions so far for this guy? I need to change the color. It's not bright enough. Any questions so far though for this? Okay, if not, we're gonna do the next one. We're gonna do the next one. Okay, let's look at this. Now we need a lower bound. We need a lower bound. Something that is strictly less than the stair, right? Remember that area is the stairs. Can you help me? Something strictly less than that. Exactly, the area of the curve below. I know you didn't say that, but I know this is what you meant. You meant the following, right? Ajahn, what about if I draw this line? Wait, that's too similar. Let me change it to blue. Blue, where are you? Blue. Okay. What about this one? I can do this, right? And then I'm gonna lift the last piece. Okay, and I'm gonna draw it straight. You can see why. You see why I want to do that. Okay, right? Which means you kind of have two things to calculate, like before, right? You have two pieces. You have this and that to calculate. Okay, so far so good, right? If we can find the integral, then it's the same thing. Okay, so let me just write here. Let me just write here. Let me move this thing a little bit. Okay, and I know that this is greater than or equal to. Actually, let me write it in the middle. Okay, so the area is less than or equal to the blue one. Oh, no, greater than or equal. Sorry, the blue and then flat is greater than or equal to the area. So that's good. Everyone clear on that, right? Let me delete all the highlights. Okay, so that means all we need to do is define this blue line and the last piece, right? So let me show you one magic. Oh, no, it's not greater, it's less than. Sorry about that. Saran, you're correct. Yes, it's this way, not the other one, right? It's strictly less than. That's what I meant. Okay, so that means you need to find the area under the blue curve. Okay, you need to find the area under the blue curve. So that means you sort of need to know what the blue curve is, or you have something smart. Anyone has a good idea though, how to figure out the area under the blue curve? Anyone has a good idea? You be my one trapezoid. You can do much better than trapezoid. Aha, very good. Sarah noticed something. That these two guys are exactly the same thing, right? These two graphs are exactly the same thing. You just shift it to the left, right? So that's good. The green and the blue are exactly the same curve, except you just shift to the left. Someone good with that, right? You shift it to the left. That is why I left out the last piece. So it's exactly the shifted graph. So the question is, when you shift the graph, what happens to the area, right? Wait a second. Let me make sure that everyone with me. So the green is this piece, right? The green is this piece. The blue is this piece up until minus the last one. It's this one, right? You can sort of see they are just shifted to the left. So I asked you, if you shift the graph to the left, what happens to the total area under the graph? What happened to the total area under the graph? When you shift the area to the left, what happens to the total area? Decrease. No, it's the same, right? What I am claiming here is the following, that this area and this area are exactly the same thing. Okay, so far so good. Right, we have the first piece and the last piece and so on, but the piece in the middle here are exactly the same thing. Okay, they are exactly the same thing, which means, right? So this is whatever answer I have before, which is what? 2 square root n minus 2. So this thing gonna be 2 square root n minus 2 from the integral, right? From that integral. Okay. The consequence just 2 square root n from that integral. Okay, and then plus the last piece, this piece, right, which is 1 over square root n, is less than or equal to the area. Someone with me though? Is someone with me? Okay, so we agree, right, that the area under that little piece on the left and the right here are exactly the same. And I know that this is that area. Okay, and the last piece over here is exactly 1 over square root n by definition. So we have the lower bound, a pretty good one as well. Keith, are we good? Or any particular path you are wondering about? Okay, good. So we have the lower bound. The lower bound looks like this. The lower bound looks like, let me copy it, 2 square root n, 2 square root n minus 2 plus 1 over square root n. Okay. So that's good. So this technique is called the integral bound. There are other kind of bounds if you try to be a little bit smarter and so on. Okay. So that's good. You may think, okay, Ajahn, this is a lousy bound. No. This is a really good bound. Think about it. Think about it. If I try to ask you, okay, please sum up from I equal to 1 to n. Let's say n is 1,000. Actually, let's make it 10,000 because that way I can square root. Okay, let's make it 10,000 of 1 over square root n, 1 over square root I, right? I don't know what the value is. You can get Python to do it, right? But I don't know what the value is. But one thing I know is that the sum from I equal 1 to 10,000 of 1 over square root I, right? This thing is going to be less than or equal to 2 times square root of 10,000 minus 1 and greater than or equal to 2 times square root of 10 to the 4 minus 2 plus 1 over 100. Okay, so that's good. Let me calculate the number for you real quick because this one is easy enough for me to calculate. Sorry about that. This one is easy enough for me to calculate real quick. So this thing is 200 minus 2, right? 200 minus 2 plus 1 over 100. So this thing is what? 998.1. 0.01, sorry about that. 0.01 less than or equal to, it's 1 over square root 10,000. Sorry about that. 1 over square root 10,000. So it's 100. Huh? And this is our sum. 1 to 10,000. Less than or equal to 200 minus 1, 199. Not bad, right? Not bad. If you think about this, you can tell it up to a really good accuracy. Not bad. Why can't we say it's less than and not equal? Yes, you can say that. I'm just trying to be safe here, because if your integral matches exactly with the stair, then yes. You can say that it's strictly less than. Works too. Works too. But I want just to show you that the technique for you to bound the sum is, one of them is integral bound. Okay. That does happen too. The integral is the same as the sum. Yes, the integral, if you remember, is Riemann sum. Right? Integral is Riemann sum, which is kind of sum, except your piece is a lot smaller, right? When you integrate, you're not gonna do this, right? At least you're gonna use midpoint rule or something. But Riemann sum, when you do the integral, it's a very finely shot, right? It's a very finely shot. So it's closely related, but not quite. Any questions so far though? Any question? I think this exercise is very easy, right? This exercise is pretty easy. Does that mean integrating over more increasing? No. Depending on whether you increasing or decreasing function, our technique got missing piece, right? So can it be equal? What's the missing pieces? You mean this little guy, the missing one? If you know exactly what to subtract, then yes, they're gonna be equal. Except it's kind of hard, right? This is why typically, for those of you who learn numbers, this is why we do trapezoid to actually approximate that missing piece. We do a trapezoid rule to approximate that missing piece. We do this, actually, we do this to approximate the missing piece. We hope that this guy and that guy are going to cancel out. That's what we hope. Okay, typically you do the middle one, and then you draw that, and then you hope that the thing that you over and the under are going to cancel out. Okay, so far so good. Then I'm just going to leave this in the middle. Okay, but you can continue on your own for this one. You can actually approximate something that looks very magical, like n factorial. Right? We learned that n factorial is like n. So for example, 10 factorial is 10 times 9 times 8 times so on, times up to 1. Okay? We can approximate n factorial as well. And then you may ask, Ajahn, n factorial is not a sum. We learned about the sum, but this is not a sum. Anyone has a smart thing to say? How do I turn this into a sum? Very good. We have something called the logarithm, right? So if we can bound this, right? If we can bound log of n factorial, okay, which is log of n. Oops, actually, let's start with log of 1 plus log of 2 plus log of 3 plus dot 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 plus log of n. Okay, so you can turn n factorial into a sum, and if so I show you that this guy is a sum, which means you can use integral bound to do this one as well. Log is the inverse of the exponent. But the most useful property of log is how to turn the product into the sum. That's the most useful property of logs. The reason it's useful because in most of the combinatoric, which we're going to learn next week, and most of the probability, for those of you interested in data science, things typically multiply together. They do not add each other. Think about all the physics law. Think about all the physics law, like F equal to ma, right? Or F is gmm over r squared. You never see the following: g plus m minus r squared plus 2. You never see physics law that looks like that, right? Most of the law looks like power law, and the most useful property of the log is actually to turn the product into the sum. Okay, I think I taught people in numerical method that if you can turn log into a sum, you turn really hard problem into really easy problem. Okay, so that's actually the use of the log. If you want to use a value, which one would you use, the upper or the lower? Actually, the average might not be bad, right? Right. So the property of log looks like this. Keep log of a times b is log of a plus b. You can prove that on your own. I'm not going to do it here. Okay. At least you have seen it. At least you have seen it. It's straight from the definition. Okay. So that's good. And another question: which value would be used? Upper or lower or average? Actually, neither. Actually, just report the bound. It's okay. So think about this. If you know that there's a line in between, right? You report the upper bound, lower bound. That's way better than report the average, right? There's some missing information whenever you report the average, and that's actually what most people are doing, and you're throwing away information. Okay, giving them the average is okay too, but better one is to give them the range, right? So for example, your COVID-19 vaccine, a lot of people are going to say, okay, it's 70% effective, 50% effective, or Sinovac 61% effective or something, right? That means nothing if you do not put the error bar on it, like 60 plus or minus what? What is your confidence interval and so on? That's a good. So don't throw away the information. Except only when you try to convince some higher up, and you know in Thailand the higher up they do not get the position because of their abilities of the fact that they are smart, right? So that means you should expect higher up to be stupid. So dumb it down to something that they can understand because you need to convince them to sign something. I think that answers your question, Thanakat. Thursday is not a holiday, but Friday is. Wait, it's Thursday. They wanted to make it a holiday, right? And I say it's not a holiday, so we're gonna have class on Thursday. Whatever they said, right? Except when you just throw it away, right? Like when n equal to 2, right? Right. When they you know, sorry about n equals to 2, right? N equal to 2, they did the right thing, except they did not say the right thing. They have the data, they show the data, except they happen to like calculate some confidence interval, which is like shitty. Okay, they did the right thing though. As a doctor, you should test on it. Thursday is not a holiday. There is one Thursday that they try to make it a holiday, but then I'm gonna do a makeup on that day. There's one of them. I don't remember which one, but there's one Thursday that is a holiday. I checked early on in the term to make sure that there's no holiday for you guys. Okay, now I have 10 minutes. I want to teach you something really simple. But you can continue, right? But you can continue, right? The fact that if you turn log of n factorial into the sum already, you can calculate the upper bar and lower bar. You can look in the lecture notes. I just want to show you that it's actually very generic, and then you're gonna get something, some bound. There is also a thing called, if you're interested, and this is not about the sum though, something called Stirling formula. Like they say something like n factorial is e to the 2 pi and a whole bunch of other function. E to the pi n plus n or something. I don't remember. But you can look up Stirling formula. It's just like this, except it's a lot more accurate because someone actually figured out. Raheem Sterling from Man City. No, Sterling. I think it's the same guy as Sterling Engine. I hope it's the same guy. I haven't checked though. You should check. It's called Sterling Formula. He was a physicist, and I think half the physicists way back then was a monk, not a monk, the guy at the church. I don't know what it's called. So the guy at the church way back then was really cool. Most of them are mathematicians. No, they call it something else though. I don't know. I don't remember. There's a word that I don't remember. It's on the top of my lip, but I don't remember. Okay. They do something really cool, like Pascal guy or Bernoulli guy. They are all those people. They were cool back then. Okay. Okay. Another thing, I want to teach you something really quick. Okay. A lot of times, right? We are trying to understand the sum. Like so, for example, this sum. Where is it? We are trying to understand the formula when n is really large. So, for example, the thing on the left over here. We are interested in the behavior when n is large. Okay. When n is large. Okay. And this is what we call asymptotic behavior. Okay. Okay. And this is a very important concept in computer science because most of the time when you say how fast is your algorithm, right? You're not going to tell them exactly what is the running time, right? 10 seconds, 20 seconds or something. But you're going to tell how does the running time scale with the number of sample, right? So this is the behavior when n is large. Okay. How it scales when n is large. Think about this, how it scale when n is large. Okay, let me get your intuition first. Think about this. This term over here, the lower bound, when n is large, what do you think it's equal to though? What do you think when n is large? What's going to happen to that term? Risky, use your physicist approximation. When n is large, what would you call that term? If n is large. N is large, it's not approach zero. No, not minus infinity. Big N. No, but when n is large, but it's still some finite number. So think about this. When n is large, right? 2 square root n minus 2, 1 over square root n, plus 1 over square root n. When n is large, think about each term. That thing is like 0. Right? Right. That thing too, but I know this thing is going to be large. Large minus 2 is still a large number. So this thing is going to be something along the line of square root n. Again, I want to see this is not official symbol though. Okay. The official symbol is actually it's called theta of n, but you get the idea, right? I'm going to teach you about the official symbol later, but I want you to get the idea that when n is large, there is a certain behavior that it's going to behave, right? That this term going to be like negligible. Minus 2 from like, if you have like a million baht, square root a million, that's a million, right? And then you minus 2, you don't care. So you're going to call that a million anyway. Okay, so that's good. So this is what we try to get at. This is called the asymptotic behavior. What happens when n is large? Okay, how does it grow when n is large? Okay, so that's good. So let me give you a whole bunch of definition, which I forgot as well. But in the exam, you have the table. It's open book, so you don't really care. I need the table real quick, and I open the table, except I closed it already. Because I don't remember the definition as well. There are like 7 of them. I remember 2. 2 seconds. Okay, doesn't like my password. Maybe it doesn't like my password. Or maybe my keyboard is. Okay, seriously. What language is my keyboard in? 2 seconds. I opened it already, except I cannot find it. Where is it? Okay, there. File. Notes, and let me just copy it from the lecture note. 2 seconds. Okay, now I have this. Don't worry about the table here because it is, and this is why I use Mac. I can paste the image right from my computer. Okay, don't worry about memorizing this table though. I just want to show you some of it. This table will be given like this open book anyway, so you just open the lecture notes. Okay, it's on the lecture notes. So asymptotically, typically it says the following that think about look at this. Most of them, right, gonna have limit x equal to 0, and then you want to compare two functions. So for example, when we say 5x squared plus x plus 2, okay? So this is your f of x, and I want to say to check whether it is growing like 5x squared or not. Okay, so think about this. It makes sense, right? It makes sense to say that these two guys grow exactly the same way, right? So think about the first definition. Okay, it say that they are asymptotically equal. So that means as you go far away and far away, these two are essentially the same. Okay, so the way to check is this. Okay, the way to check is this. To check whether f of x is similar, asymptotically equal to g of x, right? You calculate. The actual definition is it means that the gap is really close. The gap is close. The gap is infinitely small compared to its value. Okay, so limit x goes to infinity, right? Of fx over gx, it should be 1. Right? So that means all you need to check is 5x squared plus 2 over 5x squared. Right? Which if you still remember how to take the limit, right? So when x is large, you can ignore x and 2, right? Because there's a 5x squared over here, and then you're left with 5x squared over 5x squared. Right? 5x squared or 5x squared. So that's going to be 1. Are we good? Right? So the limit of the ratio is 1. So that means we can typically, we write that 5x squared plus x plus 2 is asymptotically equal to 5x squared. Okay, but no one actually do this. The two most important one for you are this guy and that guy, which we're going to discuss. Okay, so we can also say the following, right? We can also check whether the two function as x gets large, okay, is f going to be strictly less than g? Okay, if f going to be strictly less than g. So if f is less than g, right, you think about this, f over g, okay, it's going to be less than infinity. This means it's finite, right? If f is less than g, right, this thing will not grow to infinity, right? Even though both of them are going to go to infinity, but the ratio will not go to infinity. Okay, so which means the easier way to check is to check whether the limit is it finite. So yes, that means we can say that 5x squared plus x plus 2 is O of 5x squared. So that's good. So the definition is this guy, but the intuition is this. Okay. So the reason that we care about this one right? Is that this is the typically this is the class of running time you probably see OX squared, right? You typically see it without the number 5. Okay. The reason is important because it means that this thing is in the same class of running time as the X squared time called quadratic running time. Okay. Let me say that again. I think if you're not CS major, then you're gonna confuse why do we care about this. Okay. So the goal here is to understand the asymptotic behavior. Okay. So asymptotically, two functions can be either equal, right? Equal. There are many equal. There are this guy equal, that guy equal. Okay. They can be less than each other, right? One is less than the other one, or one can be greater than the other one. Okay. At when n is large. Okay. So the way that we check this is to check, right? Is to check the limit of the two functions. Okay. If to check the limit of two functions. Okay. When x is large, the two function, right? If g, if let's think about this. If f of x is growing faster than g, okay, let's think about the easy case. If f of x is growing larger than g, for example, we know that x squared is growing faster than, I don't know, 99x. Okay, right? When x is large, we know that x squared is growing much faster than g of x. So the way that we want to say that this thing is growing faster than that, so we check the limit f of x, which is x squared over 99x, right? Because if this thing is going to be much larger than the below, right? This thing going to go to infinity. Okay, this is the way that we say that f is greater than or equal to g asymptotically. Okay, are you good, Keith? So this is one example of how we compare things asymptotically, but there are like a lot of symbols for it, which we're gonna do next. Okay, are we good? So the intuition is this: you want to compare asymptotically the two functions. Which one is growing faster when n is large? Okay. Why do we need to do this? Because typically when you try to analyze the algorithm, okay, when you try to analyze the algorithm, do not care when your data is small. Think about when you try to join two tables or try to join two Excel, right? When n is small, it takes no time. But when n is large, you want to know how it scales. Some programming problem is hard because the runtime is O(n) square, right? So we care what happens when n is large. Okay. So for example, the for loop that we did last time, right? Right. So I want to see if you try to sum this thing up like you did last time, right? I times j. If you try to sum this thing up with the nested for loop, right? The runtime, if you try to run it a million times, then I know that this thing grows like n squared. Okay, that's going to be +1, -1, and so on, but I don't care. Okay, as long as the leading term is n squared. This is the behavior that we see, right? And then you compare it when you do the algorithm much smarter way that you do sum of I, you know that these two guys are equal, sum of j, and then you multiply each other. You know that the runtime of this grows like n. Okay, and then you want to compare which one is faster, right? You want to compare which one is faster. So the way you compare it asymptotically, right? When n is really large, which one is faster? Okay, it's clear. This one can be a lot faster, even though there might be some setup cost, right? It could be n squared plus 100, but I don't care. But when n is large, the right-hand side is much better, right? Wait, I should add 100 to this guy. It could be n plus 100. But I know that when n is large, the right-hand side is much faster than the left. And we only care about when n is large. Okay, when n is small, it's typically fast enough for you to read. Okay, are we good, Keith? You may not appreciate it now, but if for those of you who gonna learn data structure, you're gonna appreciate this. We only care about the behavior asymptotically. Okay, so let me get rid of this. And let's get back to the table. Oh, I should not erase it. Yeah. Let's get back to the table. Let's get back to the table. Let me teach you something really quick. So this is going to be like free problem in the exam. So think about this. If you have two functions, okay? So we have, not really. Quantum, you don't really care about runtime. Just get the correct answer is hard enough. Just get the correct answer is hard enough. So let's do this. Okay. So I want to see what is the asymptotic behavior of this guy versus G of X G of X. Okay, before we go on, let me talk you something about Nobel Prize of Physics this year. Because Risky touched on something quite important. The Nobel Prize for Physics this year is about how to compute a complex system, about the computation of complex system. So if you learn physics, right? Everyone learn physics, and you're gonna see all the physics. Okay, Ajahn, you simplify a lot. You say a car is on the road. You ignore the following, that the air is running through the car. You ignore the fact that the car has so many parts that has to run together. It emit heats and like a whole bunch of other things, right? So when you do physics in high school or in mathematics, in high school or even in like university, right? All the problem is simplified. So think about this. The science is like that at least 3 levels. Actually 4. Let's think here. Let me draw physics over here, right? Physics, there's a chemistry, which is a higher level, right? So base chemistry is actually the physics of all the molecules, right? The physics is all of molecule. If you know physics, you know chemistry essentially. And if you know chemistry, you know biology, because biology is like higher order system, right? It has more complexity because it's interplay of all the molecules, which if you think about it, it's really physics. So physics is actually one of the most fundamental things, except when you learn physics, when you learn quantum, if you learn quantum, I suggest you take a quantum class, everyone. If you learn quantum in physics, for example, you can only solve like 5 problems. Can only solve 5 problems in quantum, which is hydrogen atom, and that's it. Hydrogen atoms, right? Helium is like so hard. There's a quantum class, Risky took it. Right. You can do hydrogen atom, and you know hydrogen atom is like 1 proton, 1 electron. That's it. There's a missing link over here on how to go up from physics to chemistry. There's a missing link. There's a missing link because it's too complicated, right? It's too complicated. It's too complicated. If you have 3 atoms already, you're done. Think about your ion. It has like, I don't know, Keith, you can correct me. It has like about 20 protons, right? And maybe 20 electrons. I don't remember the number, but that's too complicated. There are like 21 of them. But if you think about it, biology, if you're talking about things in grams, there are 10 to the 23rd molecules in it. It's a complex system that you have no idea how to calculate. That you have no idea how to calculate. So the physics Nobel Prize for this year is the missing link. We are not there yet, though. We are like there. We are there. We are not there yet to go from physics to chemistry. We are not there yet. Right? The missing link is very important. And I think in the next, at least next 50 years until I die, it's gonna be the human knowledge should focus on this, on get all the missing link, right? All the missing link. Okay, so that's enough. Let's come back to the mathematics, the boring part. I think that should give you some idea about, yes, human knowledge come so far, but there's a lot more to go. Okay, we have solved a simple problem, but for complex system, we have no idea how to do it. And this guy has some idea how to do it, but I haven't read the details, but I got the high level picture. Okay, so let's come back to our mathematics. Okay. Oh, by the way, when I draw physics over here, mathematics is like over here. It's like more fundamental than anything, but it's disconnected from the rest. It's math is here. Physics is here. Like physics is like with the friend, right? Chemistry and biology, which there's a real path. For this one, yeah, not really, not a real path. But it's a much more fundamental than everything. Okay, let's come back. Let's come back to this one. What about me? I don't know. I just do whatever I feel pleased to do, like teaching you guys how to scam people. That's I feel pleased to do. So let's do this one. I want to answer the following question. Is F asymptotic? Oh my God, the pen. 2 seconds. The new iPad OS, if you have a chance not to upgrade, don't upgrade it. The pen lags so bad. Okay, I want to answer the following question. Is F asymptotically equal to G? Is F in O of G? This is called big O. And is F in little o of G? F in omega, oops, omega of G, or F in omega of G, F in theta of G. Okay, that's good. We just want to check whether it satisfies the following question. Okay, the important one that you care that you're going to see in the Dankanat class as well is this guy and that guy. Mostly this guy, mostly like 99.9999% of the time is that guy, is the big O. Okay, so to check that, it's very easy. So think about this. Everyone just asked you to check the same thing, right? The limit of f over g. So limit of 5x squared plus x plus 2 over x, right? This is just the limit of 5x squared over x, which is infinity, right? I hope everyone knows how to do the limit, right? This thing approaching infinity. Okay, so that means let's check. Is f limit is this guy infinity equals to 1? So it say no. So this guy is no. So not. So no, f is not asymptotically equal to g. Okay, and then you check whether infinity is it less than infinity, right? So you say no, right? Infinity is not less than infinity. So this thing is say only if it's finite. Is infinity equal to 0? No. So little omega, yes, it just asks that it is infinity. Yes. And then you ask, okay, is infinity greater than 0? Yes, it is. Right? And no. So only two things. So the property that is satisfied is f is in little omega of g, and f is in big omega of g. Okay. So I get that out of the way. So if this problem come up in the midterm, it's a free problem. I just need to teach you so you know that there are a whole bunch of symbols to compare asymptotic behavior and there are intuition between them, right? You can go read lecture note if you like. Okay. Any questions so far though? Any questions so far? Any questions so far? The use is actually used in typically in algorithm analysis. How good your thing is. Okay, the asymptotic behavior. Yes, you're gonna see people do this. Some people are gonna write like this. It's the same thing, but it's not correct. Okay. Why is last one false again? Oh, it's asked whether it's equal to some constant. That is not 0. So the last one, it should be like 5 or 10, not infinity. And not 0. Okay. Okay, that's good. Any other question? Some people are gonna write like this. It's not correct, but it's acceptable. This is like most wrong, but popular. Let me say that. Wrong, but popular. Okay, so some people are gonna write like that. The correct way to write is this because O of G is actually a set. Okay, it's a set of function that has exactly the same growing behavior. Okay. Any questions so far though? Any questions so far? If not, we're gonna take 10 minutes break and come back real quick because I want to teach you something fun. So not how to scam people though, like how to play actual games. Hey everyone, and let's come back at 15:15. And why is my keyboard lacking? Can you please also give us some hint on 456 at the end of the class? What is 456? What's 4 about? Can you tell me what's 4? I think I give the hint to every single problem though. It's for the chessboard though. 5 is a chessboard. So the chessboard, you just play the game, you'll see. Try to keep track of the number of black and white and see what you got. Just show that every move preserved the invariant and you're done. Just show that your all the move preserve the invariant, but the goal for this the goal for this week is actually to figure out what to prove. If you figure out what to prove, then it's like not many lines proof, it's a straightforward proof. Okay, so for the chessboard, keep track of the number of black and white as you play. Then you'll see something. And then prove that fact that you see. Yes, there can be multiple invariants. Any valid proof is accepted, don't worry. Number six. Number six is like the hint said, try modulo of 3. And number 4, I don't remember what is it. Is it the yo-yo one or what is it? Or is it the circle one? It's the circle one. Ask for the spoiler on Discord though. For number 4, it's if I give you the picture, it's a spoiler. It is very spoiling, so I don't want to give it here. Not really. Not really. You might be able to get away with that, but no, not really. Number 4, if I give you the hint, it's a spoiler-ish. Ask me on Discord if you want it. Do you want a spoiler though? A lot of people probably doesn't want a spoiler yet. That was close though. Whatever you said, Justin. What you just said, it's close. Close. Do you want a spoiler though? If you have a spoiler combined with whatever you have now, you're gonna solve it for sure. But then you're gonna feel bad for the part that you got spoiled. You're gonna solve it once you have the spoiler for sure because you have the other part already. It's very close though. What you had is very close. Yes, it's really close. There's the other half, which if I draw one picture, you're gonna get it really quickly. Easy way is that you don't. But yes, there is a Tixie, but it's not easy. There's a way, but it's not easy. What I recommend you to do is just to draw it somewhere else and then use an image and then put the image on the latex. There's a way, but it's not easy. Tixie, yes, give me headache as well. If you ask me right now to write Tixie, I have no idea. Then I go read the manual every time. All your lecture notes and all your homework and Tixie though. That's why the picture is so sharp. The picture is so sharp, but his name is not though. His name is not. Copy the image. And why can't I paste it here? Aha, there. 15, 15. We got it, right? Okay, wait. It froze. Okay, so let's do this real quick. What we're going to do next, let's consider this problem. The problem is called Tower of Hanoi. Some of you may have played already. And it looks like the thing that I tried to paste, except it doesn't come. So wait 2 seconds, let me show you. Tower of Hanoi. Let me show you the picture. I think you might have seen it in like the wooden toy shop and so on. Internet, you're not my friend at all. What? Wait, what? Why am I muted? Is it better? No, it works, right? I don't know. I got kicked out from Zoom of my own. Okay, this is what it looks like. So you have, typically you found this in a wooden toy shop. I bought it once and I put in 149 and I think it's now moved to 1502. And I think you're gonna see, you see this somewhere in that room, right? There are 3 sticks. Really? Oh, now that's better. Okay, now that's better, right? Okay, now that's better. Okay, so now it's question about what happens. So this guy is Tower of Hanoi. So you know how to play? So the way you play it. There are, wait, let me spend 5 minutes. There are people who call audiophile, which is like they buy expensive speaker and headphone and so on, and they and yes. So for analog circuits, there's a real difference between a good one and a bad one. But then there's a shop. There's a really famous shop in Thailand. Try to claim that a 10,000 a LAN cable, 10,000 baht LAN cable is better than like typically you buy it like 100 baht. 100 baht is already expensive. It's like 50 baht typically. 50 baht. And then if you know a little bit about electronics and you know immediately it's bullshit, there's no way. Go search for like LAN cable drama and then you're gonna see. Not only in Thailand though, in US as well and in a whole bunch of country. And that same brand tried to sell it in Thailand. Just buy a mid-range one. Mid-range. Don't buy the low quality one. Buy the mid-range one. I think that's good enough. That's like way. So the quality and the price it looks like this. So if you go from like low to medium, it's like diminishing return. So just get it here. This thing is like diminishing return. This thing might cost you 100,000. This thing might be like 10 million. There's a diminishing return over here. So this thing might cost you 1,000 or 2,000. Okay, so go back to Tower of Hanoi. So the way we play the game is the following: is to because I do not have the real thing for you. So 5, 4, 3, 2, 1. So there are 3 places for all these numbers. Okay, the way you play it is you can move this guy 1 piece at a time. So you can move 1 over here, then you can move 2 over here, but you cannot move 2 over here because 2 cannot be on top of 1, right? The bigger number cannot be on top of the smaller number. Okay, and then the goal here, now you kind of know how to move, right? Then you can move 1 over here, move 3 over here, and so on. You can continue playing this. But the goal here is the following. But the goal here is to move all these 4 or 5 pieces to the other one, right? So that means I want to go from 5, 4, 3, 2, 1, and then there are 3 places, right? I want to go from here to 5, 4, 3, 2, 1 to another one, to another stick, right? And then the question that I want to ask is how many turns it takes? How many move is required? Yeah, so far so good. Everyone understand the idea, right? I can continue playing this. So for example, you can move 1 over here, to move 2 over here, to move 1 over here. Now you can move 5, you can move 4 away, right? And so on. Okay. Exactly. If you think about this as a recursion, you are now learning something in this class. You never do the work by yourself, right? You use your friend. So let's think about this recursively. Let's think about this. Okay. The way, if you learn something in this class, don't put on the work yourself, use your friend. Okay, how do I solve this? What do you think? What kind of friend do you need? That's the first question. What kind of friend do you need? You try to solve the problem with like 5 stack, right? With 5 numbers. A smart one. Very good, right? Very good. But if I have a friend that is a little bit dumber than me, right? That means I'm gonna show that I can solve 5, but I will need the friend that is a little bit dumber than me. Let's say there's a friend who knows how to move all these 4, right? All these 4 to another one. I don't know how many turns it takes. So let me do this. Okay. This is by your friend. I don't know what the details, what my friend did. I have no idea. Okay. So let me write this. Let me write T of 5. This is the number of turn. I need to move 5 to another step. Okay. So the first thing that I did, right? I hire my friend to move the 4. Okay. I hire my friend T of 4. Okay. And then what do you do next? What do you do next? You hire your friend. And then what do you do? You move the number 5 to another one. Oops, sorry about that. You know, number 5, right? So that means it's a +1, right? You move number 5. So fast good, right? They say move number 5, you +1. That's another turn. Then what do you do? Then what do you do? Very good. Then you hire your same friend to move all these 4 back to the top. Are we good? So we have the recursion that's written like this. Is everyone good, right? The idea is you don't solve it yourself. So the thing that you get, right? The thing that you get is going to be T of n, right? The number of turns to move n pieces is T of n minus, oops, sorry about that, 2 times T of n minus 1 plus 1. 2 because they're these guys. Okay. So 2 of Tn minus 1 minus 1. I mean, why do we need 2t? So the first t is for the first move, right? So let me repay. So the first t is for this move. Okay. And the number 1 in the middle is for that 5. Okay. And t4 is another one that you need here. Okay. So it's 2t4. So fast good. But at the end, right, you need some base case, right? You know, you cannot just do this. You need some base case. Okay, so that means how many turns does it take to move 1? Well, you can tell it's 1, right? If you have only number 1, it takes 1 turn. Okay, so let's tabulate this. Let's tabulate this. Okay, so T of 1 is 1. What's T of 2? Can someone tell me? It's good. It's 2 times 1 plus 1, which is 3, right? T of what? 3 is going to be 2 times 3, right? 2 times T2 plus 1, which is 7. T of 4 is, sorry about that, is what? 2 times 7 plus 1, which is 15. And T of 5 is 2 times 15 plus 1, which is 31. It's not n minus 1, it's Tn minus 1. T of n minus 1. So let me draw all the connections, right? The 1 is here. 7 is here. 15 is here. Right? This is how much you need to hire your friend, like 15. Everyone get? Actually, Keith, you didn't take a class. The class gonna prove that you cannot do it in 30 moves. This is actually the absolute minimum, unless you cheat somehow. Okay, so the real question is what's T of n, right? So that there are two things, right? T of n, you can say, okay, at hand that's like 2t of n minus 1 plus 1. That's not cool, right? The cool thing is like the cool thing is a closed form formula like T of n is n squared. That would be cool. But no. What do you think? T of n is like log of n, e to the n. That's a cool number, right? So what is this? What's T of n? Can anyone see it though? 2 to the n. Combine your two answer and then you're done. Thank you. Right. Well, if you stare it hard enough, you're gonna say, okay, 2 to the n minus 1. But of course, not everyone is smart as Karit, right? Like if I stare this, I have no idea what to do. Okay, let's do it like dumb people. This is the smart people way, right? You stare at this and then aha, that's easy, right? Once you know the answer, that's easy. Once you know the answer, that's easy to check, right? But no. Let's try to do it like dumb people, like me. Okay. Okay. So the way we figure it out. Okay. The way we figure this out. So let's try to figure out. Let's pretend Karit doesn't exist. Let's pretend this one doesn't exist. Okay. Pretend we don't know this. We have no idea. Okay. So if you think about this, these two. Okay. Let's pretend Karit answer doesn't exist. Okay. Typically, if you know, if you know me, the way I do things in a very simple way. I never do something very complicated. I try to do things in a very simple way because I'm not that smart. So I try to do in a very simple way. Okay, let's do things in a simple way. Okay, and actually figuring out simple way is actually smart. So I don't know. Well, so if you work with me, if you work with me for a while, you see, I said, okay, this is a very stupid algorithm, and by stupid I mean it's really smart though. Okay, something stupid is that something that you know that it works right away. So, but you never thought about it. So it's a stupid one, except the guy who figured it out is a very smart one. Okay, so smart people are gonna figure out a simple way to do it. So let's do it in a simple way. So if you think about this, let's say we try to solve T4. Okay, let's try to solve T4. The thing that you're gonna do, right, is you say, okay, John, that's easy. It's 2T of 3 plus 1. Okay, and then you're gonna Dan, you just need to keep expanding. But I want a number. I want a number. You're gonna keep expanding, right? But let's keep expanding. It's 2T of 3, right? I know the T of 3 is 2T of 2 plus 1. Okay, so plus a good. And then don't forget the plus 1. Okay, so let me write this. So this guy expand to 2 of this guy. And then you try to do that again. It's 2 to the 2, right? T2 plus 2 plus 1. Do not simplify. This is important. Do not simplify. This is a very important point. Do not simplify. It's so tempting for you to simplify, but don't. So this guy is going to become 2 to the second, right? Times T2, which is 2 times T of 1 plus 1. Okay, plus 2 plus 1. So now you're going to become is 2 to the third plus 2 to the second plus 2 plus 1. Okay, so far so good. which means I think you can guess this is not a proof in any way. This is not a proof in any way. You can guess, right, that, okay, maybe Ajahn, T of n, okay, is going to be sum I, right, 2 to the I, from I equal what to what? Can anyone tell me? From I equals what to what? No, not 1 and not n. Think about this. Your n is 4, right? Your n is 4. Very good. 0 to n minus 1. Okay. Which the thing on the right, even if you write like this, you kind of know, right? You kind of know that you know the closed form formula of this guy. At least we need to figure out something out, but we know the closed form formula for this guy. And from the seeing the pattern, this is it. Again, this is not a proof. We might show the proof next, but not. This is clearly not a proof. Okay. Okay. So let's guess the following. So T of n. Now we know it's 1 plus 2 plus 2 to the second plus 2 to the third plus dot 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 plus 2 to the n minus 1. How do we find the closed form formula for this guy though? And this is why I also tell you not to simplify, because you should get it as a sum of some sort. Okay, what do you think is equal to? What do we need to do though? What do we need to do to figure out the value of this of Tn? Anyone has a good suggestion? Yes, just multiply by 2. So you know that 2 T of n, I can just call it P. Let me save some writing. 2P is 2 plus 2 to the second plus 2 to the third plus dot 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 plus 2 to the n minus 1 plus 2 to the n. What do we do next? What is this guy? Close. No, close, but no. It's T of n minus 1, right? So it's P minus 1 essentially. That thing is P minus 1 because it's missing the first term plus 2 to the n. Minus 1, not plus 1. Okay, now you can solve for P, right? So you figure out that P is 2 to the n minus 1. Okay, good, right? So this thing gonna become 2 to the n minus 1. Now Carit can exist, right? That's exactly the same thing as Carit. But it's a bit better than staring at the numbers and figure out the patterns, right? It's a bit better at staring at the number. Okay. Everyone see, right? You have some hope. Staring at the number and figuring out the formula is almost impossible. Okay, but this is a little bit better. But again, this is not a proof, right? This is not a proof. Okay. Then you're good. I accept that answer. If you stare at the number and you know the formula, then I'm good. Okay, so let's think about this. This is not a proof, not a proof, right? Not a proof. Let me write a proof this time, one time. And then for the rest, when we do the recurrence, no proof is needed. Just get the right answer. Okay, just get the right answer. I tell you specifically though, to make the proof for exactly one part, but not, there's gonna be like 4 or 5 problems when I ask you to solve for the recurrence. Okay, then I'll ask you specifically to prove for exactly one. For the rest, no need to prove. Okay. Because it's just mechanical, no imagination is needed. So the thing that we want to prove, right, is there are 2 t's, right? So theorem, if t of n right, is 2t of n minus 2 plus 1, where t of 0 equals to 1. And for caret, I'm going to call t of k. And tk, that caret gas, yes, we need to use induction. T of k, right? So for this t, I'm just going to call it t of h, okay? T from Hanoi game. And t from caret, which is 2 to the n, which is minus 1. Okay, good. 2 to the n minus 1. We want to show that t of h is equal to t of k. Actually, let me put I for all I greater than or equal to 1. Okay. So that's good. There are two t's, right? The t that we guess from caret and the t that we know actual physical behavior behind it. That, okay, we use a friend and then we move one and then we use another friend. Okay. So we want to show that these two guys are equal. Okay. In the lecture note, I think I might use the same symbol, which make it so confusing. Now I use different symbols. Okay. So we want to show that t from Hanoi and t from caret are exactly the same thing. So help me. You're now expert on doing induction. How do we do this? Oh, by the way, I forgot to tell you the name. The name for this kind of equation is called recurrence. Don't look up the Thai translation though. It's funny. I think they call it สมการการเวียนเกิด recurrence, which I have no idea what it meant the first time I read it. The Thai translation of recurrence is funny. When Thai people, there is an actual organization that is in charge of translating all the technical words, and they typically do a really poor job. They typically do a really poor job. Yes, they translate it into something called reincarnated equation or something. Okay, the actual English name that everyone knows is called recurrence relation. Okay. Okay. It means that your function depends on like whatever your friend returns. It's like recursion as well. So the proof, the base case is easy, right? Base case, I think everyone agree. T of 0, you plug 0 in. Wait. Let's get the predicate first. Predicate. Right? The predicate says the following, right? That P of I is to check whether T of H of I is equal. Note the double equal though. This is comparison. Is T of K I. Okay. And the base case, that would be easy. Right? That means I need to check the 0 for each one of them. TH of 0 equals to 1 and TK of 0 is equal to 1 by definition, right? It's 2 to the 0 minus 1. No, T of 1, sorry, not T of 0. Sorry about that. T of 1 is 2 to the 1 minus 1, which is 1. And that means T of H of 1 is equal to T of K of 1. And then we are done with the base case. Now we need the inductive step, right? Okay, let's fit everything in one page. What do we assume and what do we need to show? What do we assume and what do we need to show? Anyone? What do we need? What do we assume? Okay, both is true. Oh, now what? We assume that T of H of some number K is equal to T of K of some number. I should use some other number. Who else? N is bad. J for Justin. Good. T of J for some J, right? For some fixed J, for some fixed J. And then we want to show that T of H of J plus 1 is equal to Tk of J plus 1. Okay, good. Right, but I changed the number to J because I used K over here already. So we ran out of symbol. We used J instead. How do we show it though? How do we show it though? Anyone? The right hand side, what do we know about the right hand side, or what do we know? Right hand side. So let's look at this. The right hand side, Tk of J plus 1 is equal to what? Fixed J, or for some J that works too. For some J that works too. You don't need the word fixed, but I write the fixed for. Okay, so can anyone tell me what's Tk? The T caret of J plus 1. Good, it's 2 to J plus 1 minus 1. Okay, let's leave it there. Let's leave it there. That's what we want to show, right? By definition of this guy. Okay, so what about this? Tn of J plus 1. What do I know? What do I know? This is the left hand side. What do I know? T of H of J plus 1. What do I know? Very good. It's by this definition, right? The high noise T needs to follow that guy. So it's going to be 2, oops, 2 times T of H of J, right? And then plus 1. What else do I know? What else do I know about TH of J? What do I know? Wait, why is it -2? It should be -1. Sorry about that. Right. So this thing is by inductive hypothesis, right? So we know the TH of J is TK of J. So it's going to be 2 times TK of J plus 1. What else do we know about TJ? TK of J. So this is by definition. What do we know about TK of J? Oh, I keep missing all this little symbol. What else do we know about TK of J? Good. It's by definition, right? By TK definition, it is going to be equal to 2 times 2 to the J minus 1 plus 1, which is equal to 2 to the J plus 1 minus 1, and which is equal, and then we're done. Okay, so this is the actual proof. The staring at the number and coming up with the formula, that's not the proof. The proof is this one, right? Or the way that we plug and chuck, it's not a proof. The way that we plug and chuck is not a proof, but it's a very good way to get to the answer, right? The way that we do on this page, this is also not proof, but it's a very good guess for you to know what to prove over here. For you to know what to prove over here. Okay, but in the homework, I asked you to prove exactly one part. You don't need to prove all the 4 parts, or maybe 5 questions. I don't remember how many questions there are. Okay, I can wrap this up because I have 5 minutes or 2 minutes. Okay, so like I said before, that the way that we did it before, it's not a proof. The actual proof is this proof. We want to show that the 2 T's are equal, right? The T that we guess from Hanoi that come from the physical situation, come from the recurrence, and the t that we guessed together are exactly the same thing, right? And by exactly the same thing, that means they both have to be equal for every single integer. Okay, so the predicate, like we proved by induction, right? The predicate here is pi is that th and tk are equal for a certain number. Okay, and the base case is the simple thing, right? So the th is what we made up. No, 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 no. None of this is what we made up. Th is from here, right? You get this from physical reasoning. Where is it? You get it from physical reasoning over here, right? The fact that you hire your friend twice and you need to do your move yourself once. Okay, we did not made it up. Okay, so it's come from the physical relation that we get to this relation, and then we can solve the exact formula for it. Okay, so and the proof is simple, right? That you assume that it's equal to the previous number, and then you want to show that it's the next number, it's equal for the next number. So the right hand side is by definition, right? It's tk of j plus 1. So it's 2 to the j plus 1 minus 1. The left hand side gets a little bit of work, right? The left hand side, t of h of j plus 1, then you use the definition that it's going to be 2 times t of j plus 1, right? By definition, right away. But we know something about th of j because of our inductive hypothesis. So we plug that in, and then you simplify things a little bit, plug in the definition of tk, and then you're done. Is th like the axiom? Th is typically easier to get from the physical situation. Okay. So we typically say that this guy is a solution to that recurrence relation. Okay, are we good? Any questions though, honestly? Yes, like your homework, right? The IS part, yes. The IS part say the following. The IS part says that TS of J and TK of J are exactly the same thing, right? By this. Okay. Any other question though? Any other question? So do the homework. The homework 4 is really hard. Do the homework. And then homework 5 is going to be a lot easier. Like lot easier. Yes. I'll work with Justin. I'll work with your friend. Don't struggle alone. The Pokemon one is confusing though. Yes. Work with Justin. You're gonna figure out. Don't struggle alone. Well, don't steal his answer though. Like I said, this class, all I care is that you learn something. Stealing the answer doesn't give you any learning thing. Okay. If no question left, let's call it a day and we're gonna see you on Thursday. Bye everyone.